Hello everyone. Today we'll discuss connectedness and path connectedness. And path connectedness. So we know that a topological space X is said to be connected if X cannot be partitioned into two disjoint open set. Okay. So U and V are non-empty and disjoint. If X can be written as this kind of disjoint union, then X is said to be disconnected. If there exists some open set UV, open set in X, such that X can be written like this, then X is called disconnected. Otherwise, if uh, if this property does not satisfy, then we'll say that X is a connected topological space. Now, what is path connectedness? So, path connectedness means, let me draw. Suppose this is a topological space X, and if we choose any 2 point, small x and small y, there exists some path which connects this space. Then the space is said to be connected. This is true for any x comma y. All x comma y belongs to x. That is, we can join those 2 points via a path. Okay. So let me define what is path. A path means it is a map denoted by gamma, a continuous map from 0, 1 to a topological space X. So this continuous map like this is called path from the initial point gamma 0. For example, this can be thought as gamma 0 and this is gamma 1, and this will be some gamma t. Okay, so the paths start at x, and at in any point any time t, there are some point gamma t like this, and this t will vary, so we'll reach at gamma 1. So this is called a path from gamma 0 to gamma 1 in X, in the topological space X. And a space X is said to be path connected if for all x comma y belongs to X, there exists a path joining x comma y, that is, which start at x and ends at which starts at x and ends at y. Okay. So let me draw some picture. So this, consider this space in R2, and suppose we remove this interior part of this circle. So the space is this. This is the topological space. We are considering this region. Now this is also path connected, right? Choose any 2 point x and y. We can always join those 2 points using a path which avoids this circle, this disk. So we are avoiding this disk. So even if we remove this kind of disk, then it remains path connected. So those are a few very easy examples. Now let us see some properties. One property is path connectedness implies connectedness. So if a space is path connected, then it must be connected. How can we see that? Suppose this space is path connected. This is a topological space X which is path connected. Now if we try to break this space into two parts, one is the open U, another is open V. If we try to write X as disjoint union of U comma V, this is disjoint union, then there will be some contradiction. So U V are disjoint, X can be written as, if we assume this is disconnected, then X can be written as U disjoint union V, and U V both are non-empty. Okay, so disjoint open subset. Then what will be the problem? So since those are non-empty, choose 2 point, 1 point from U. Suppose this is X and another point from U, Y. So now it is, we already assume it is path connected. So we assume X is path connected. Let X be path connected space. Now what will be the contradiction? So since it is path connected, we can join those 2 points by a path, right? So this is a path. Now you can see the contradiction can be seen from the picture, that if X, if this is the case, X can be written as disjoint union of UV, then the interval I breaks into two parts, right? One part comes from this U, another part comes from V. So we assume path connected, so there exists gamma interval. Interval means close 0 1. So sometimes this is denoted by I to X, such that gamma 0 equal to X and gamma 1 equal to 1. Then we can see that one part. So if we take gamma inverse of U, this is open, and gamma inverse of V, gamma is continuous map, so their union, their inverse image, inverse image of open set must be open. So interval I can be written as gamma inverse of X, right? Gamma inverse of the codomain, but codomain means it is same as gamma inverse U union gamma inverse V. But gamma inverse U is open, this is open, both are open and disjoint, both are disjoint open set. And why those are non-empty? We can see U, that is U contains the point X, right? U contains this point X and V contains the point Y. Therefore both are non-empty. Gamma inverse U must be non-empty, gamma inverse V must be non-empty. So this is a contradiction because interval is always connected. Okay, one way is to see using that. Yes, you can directly prove the fact. It is non-trivial, but interval is always connected set. So we are using this result. This is a contradiction because uh, other otherwise what is the problem? This shows that interval is disconnected. Interval can be written as disjoint union of open sets, which is wrong. So this is a contradiction. I is connected. Okay. Now let us recall what is connected components. So let X be a topological space This is topological space, and we define a relation. Define a relation. So relation is, this is one symbol for denoting relation. Define the relation by this. So x is related to y. X and y are 2 point belongs to x. X related to y if and only if x comma y belongs to a connected, this belongs to a connected subspace of x. Now the interesting thing is that this relation is actually an equivalence relation, because reflexivity is clear. X and x 2 point should belongs to the same connected subspace. This is always true. And x related to y, x just interchange x comma y. So reflexivity, symmetry, and similarly transitivity is also clear, because we know the fact, if suppose x and y belongs to same connected subspace, and y and z belongs to another connected subspace. If this is the case, we know that if a and b, two connected subspace which has a common point, here y is the common point, then the union a union b will be connected. Okay, so union of two connected subspace may not be connected. For example, consider this 0 1 union 2 3. So this is not connected. But if those two interval has a common point, then that must be connected. Okay, to connected subspace which has a common point, then that must be, their union must be connected. Okay, so that's why this is an equivalence relation. And uh, define a relation. So this is an equivalence relation. So the classes of this relation, classes of, are called connected components. Connected components. Okay. So equivalence relation, for any equivalence relation, we know there are some equivalence relation, right? So this equivalence class is, equivalence class contains all those points such that y is related to x. This is the equivalence class. So those equivalence class are called connected components, right? In our case, the class will be denoted by Cx. Okay, and note that Cx is nothing but union of all connected subspace containing the point y, containing the point x. Okay, so this should be clear, right? Because what will be the corresponding connected component? So it contains all y such that x and y belongs to the same component. So we can take all those connected subspace and take their union. All those connected subspace which contains x, and take the union. Then that must be the same connected component. Okay, there cannot be any more point. So it is clear that this is a subset of Cx, and similarly, if we choose any point belongs to Cx, y belongs to Cx, then y and that's y and x belongs to, by definition, y and x belongs to some connected subspace, but that is already included in the union. Therefore, those two things are same. Okay, so this is called connected components. From here, it is clear that X is broken into its connected components, right? Because equivalence, for any equivalence class, equivalence relation, it gives a partition. So therefore, from here it is clear that X can be broken into some connected components. For example, this will be some cx1, this is some cx2, cx3, and cx4. So those are not unique, because instead of x1, if another x1 dash belongs to the same component, cx1 and cx1 dash are same. Those two classes are same, right? Because of this relation, transitivity, this kind of property from equivalence relation. Okay. Now, similarly, we can define path connected component. So, what will be an example? For example, if we take that same example 0, 1 disjoint union 2, 3, so it has two components, right? You can see that 0, 1, this is the part 0, 1, and this is the part 2, 3. So it has two components. This one is connected by the property that interval is connected. This one is also connected. And if you add one extra point, for example, if you try to add one extra point with this close 0, 1, for example, take this point and take union with close 0, 1, then that will be disconnected, right? It is easy to visualize, but we can also prove that that can be written as disjoint union of two open subsets. Okay, so that's why those two are connected components. Another trivial example: open 0, 1 disjoint union with 1, 2. So this is nothing but take 0 to 2, this open interval, and remove the point. So we'll remove this point. Just remove this point. 1 is removed. So it will now break into two parts. So here 0, 1 is one connected component and 1, 2 is another connected component. Those are some examples. Now similarly, we can define, you can also consider Q as a subspace of R. So here, can you see what are the connected component of Q? So in this case, connected components are singleton set. So C at the point Q, it will be the singleton set Q for all Q belongs to Q. Okay, because take any 2 point, for example, this Q1 and another point Q2, that will be disconnected. Why? Because there is always some irrational number, which is, there are some irrational number belongs to which which is strictly greater than Q1 and strictly less than Q2, and that irrational number will create the problem. So we can always partition by this irrational number. For example, suppose x be the irrational number, then minus infinity comma x and x comma infinity. So here you can see Q1 belongs to this part and Q2 belongs to another component. So any two rational number cannot belong to the same component. Okay. because you can see those two are disjoint. So those two form a partition for this Q. So Q can be written as this, and Q1 belongs to the first E. So this is why this is true, because we are restricting on Q. So this is not strictly correct, because Q is nothing but this, means as a subspace. As a subspace, Q can be written as this in union x comma infinity. X is irrational, okay, irrational in between Q1 Q2. So there exists irrational. This is always true. Intersection Q, and you can see those two are open by definition, right? What are the open subspace? Open subspace means it is Q intersection some open set, but this is open in real number. So if we intersect with Q, this will remain open here, and again if we intersect this open set with Q, that will remain open in Q. Okay. So this, from this it is clear Q1 and Q2 are separated by an open set. So there, those any two different rational number cannot lie in the same component. Hence, component must contain only one singleton Q. Okay, so this is clear. Now similarly, we can define path components. Path components. So again, the same definition. I may copy the definition and replace some word. It is not copied. Copy. So instead of, so we define the relation by this, that x and y are related if and only if xy belongs to a connected subspace of x. Instead of connected, we will write a path connected subspace. Okay. So add this path connected, then again that will give an equivalence relation, and uh, the corresponding classes will be called path connected component. Okay, just include that extra path connected this. So all path connected. So again, so it is clear equivalence classes will always give a partition. So that's why X will be broken into partition. So those are some components. It may be path connected, so then there will be only one component. It is also okay, and it can broken into more parts. So some properties are like this. So one important property is connected components are closed. What is the meaning of that? So connected components are closed means why this is true. Connected components are closed. So there is some notation. For example, these connected components sometimes this condition these things sometimes are removed. There is connected components and components are same word. So you may call connected component, or you may also call components. So why these components are called connected? Because those equivalence class, those are actually connected subset. This Cx becomes connected because you are taking connected subspace and you are taking union, but all those connected subspace contain X, therefore their union will be connected, right? So that's why components and connected components are same. Components will be automatically connected. Okay, so those two are same notation. Similarly, path components are sometimes called path connected component. Okay, path connected is shorter than that, so that's why this is also called path connected components. Those are same path connected components. Okay. So one property is connected components are closed. Why this is true? Because you know that take take a subset. Suppose Cx is a connected component. Then Cx must belongs to closure of Cx. A belongs to A containing A closure. Right? Closure is bigger than A. So this is always the case. Now we need to see the reverse inequality. Something belongs to Cx closure. So what is Cx closure? So note that we know an important property. This is always true because A containing A closure. This is always the case. And we know another property. So what is the property? If A is connected and suppose A, B, there is some containment like this, then B is also connected. So B is connected, in particular A closure that will be also connected. Okay. So from here it is clear that Cx, we know Cx is already connected, but from this property it is clear that Cx bar is also connected. But Cx bar, what is the definition of Cx? From here it is clear that Cx is the maximal connected set which contains X. Cx is the largest possible connected set which contains the point X. But Cx bar is also another connected set. So Cx bar also contain X and Cx bar is connected. Therefore, Cx bar will be included in this union, right? So all connected subspace containing X. So Cx bar will automatically be included in this union. So in particular, we'll get, so Cx bar will be same as, so Cx bar will be included in the union. That means Cx bar must contain in Cx, because Cx bar is one of the element from the union, right? So from the definition, by definition, Cx bar containing Cx. So from this 1 and 2, we are getting Cx is Cx bar. That is, connected components are closed. From here, it is clear. Now, what about openness? So, can connected components be open? So that there can be some problem. For example, we have already seen these connected components may not be open. What is the counter example? Counter example for this. So again, consider Q. Here, take any Q belongs to Q. So connected component corresponding to Q denoted by CQ is the singleton point Q, right? So CQ is the singleton point. But note that this Q, this is not open in this is not open in Q, because take any neighborhood of Q, it must contain another rational number, right? So this is, let me draw Q rational. So Q will look like this kind of thing, but it will be dense. So take any rational number, take a rational number Q belongs to that line Q, then take any neighborhood, right? What is the definition of neighborhood in a subspace? It is some interval. So basis will be some interval Q minus epsilon, comma Q plus epsilon, intersection Q, right? But this must contain another point. So this set cannot be open in Q. The singleton set, that cannot be open, because take any neighborhood, it must contain some other rational number. Okay, that is the reasoning. So this is the counter example. Connected components are closed but may not be open. Now let me say when this will be open. So one condition is if the number of connected components is finite, then connected components are open. Okay. So in general, connected components may not be open, but if there are only finitely many conditions, this is one of the sufficient conditions for openness. So let us see why this is the case. So take a connected component Cx. Suppose this is not open. Okay, sorry. So we try to prove that connected component Cx will be open. So proof of this. So X can be written as disjoint union of connected components, right? Because connected that relation by connectedness, that is equivalence relation, and equivalence relation always breaks a space, breaks a set into partition, right? So Cx X can be written as some disjoint union of those components up to some Cxn. Those are disjoint union for some x1 up to xn belongs to x. Okay, so we have assumed that there are finite number of connected components. That's why we can write, we can stop after some finitely many steps. Okay, otherwise in the previous example here this is not the case. So q cannot be written as finite components. So q can, in this case those are the components q, and q belongs to rational. So that is infinite union. But in this case we can write finite union by the given assumption, given hypothesis. The number of connected component is finite. It is already given. So note that this, if this is the case and those are disjoint union, then Cx1 is nothing but x minus the complement of other thing Cx2 union Cxn. Since those are disjoint, so there is no issue. That is, no point from x1 is removed from this x, because those are disjoint. Cx1 is disjoint from other elements. Okay, Cx2 up to Cxn. Therefore, this is the case. And note that connected components are always closed, and we know finite union of closed set is closed. finite union of closed sets. So this is closed. This is closed because finite union of closed set. So this will be closed. So x minus something is closed. Let me write in. So this is equivalent to saying x minus cx1 is closed, right? So alternatively, I can write x. Just remove the part cx1. This will be the other parts. Okay, x minus cx1, it will be other parts. So x minus cx1 is closed set. So complement of something is closed, that means that set is open. Since complement of cx1 is closed, therefore cx1 is open. So from here it is clear that similarly all by the same without loss of generality I have taken x1, but you can start with x2 and xn. So from here it is clear that all connected components will be open. Okay. So this is the end of the book. Okay. So another important thing from this observation that path connected implies connected. If something is path connected, then that will be connected. So from here, a nice observation is path connected components take path connected component at x. Okay, so that will be a subspace of connected component at x. Maybe better is containing x0, containing the point x. Containing x is that will be a subset of connected components, connected component containing x. So this is true for all x, right? Why this is the case? Because the same, this is the definition, right? That path connected component. So yes, this is the definition that Cx can be path connected component Cx at for a path connected component containing x. This is union of all path connected subspace containing x. But path connected means it is also connected, right? So it is containing union of all connected subspace containing x. Because path connected means it is connected, so that will be automatically, that will be some element of this union. So there are, so path connected are already included in this union, but this is nothing but connected component at x, connected component at x. So that's why path connected components are subset of connected components. So what is happening here? So given a space x, if we take the equivalence relation by connectedness, then x broken into some parts. Okay, so those are, suppose those are connected components, some cx1, cx2, cx3 and cx4. Now path connected components breaks those space again. Okay, so cx1 can be broken into some path connected components. For example, this cx3 can be broken into connected components like this. So, and cx2 can be broken into this. Cx4 is another part, it can be broken into few parts like this. So those, now there are, so from here another observation is that number of path connected components, path components, so this is always greater equal to number of connected components. Okay, so those are some observations. Up to this, is everything clear?
Yes, sir. Um,
Okay. So let me give an example where path components are strictly greater than connected components. So in previous day we have constructed an example, topological sine curve. Sorry, topologist sine curve. So it is defined by x comma sine 1 by x. This such that x belongs to open 0 1. This said, union you can also take the axis, that y axis part, union 0 cross this interval 0 1. So it will look like something like this. It starts at some points and it oscillates, but for example it start half, then one third, one fourth, something like this. So it will be something like this. So the frequency becomes, everything is same, amplitude is same. So it is bounded between this -1 and 1, but you can see that at close to the point 0 origin, this becomes denser. This will be something like this. I cannot draw it completely, but roughly this is the space. This is the portion, this portion, and 0 cross 0 1 means the interval on the y-axis. So let me draw it with a different color. So maybe, okay. So this part is also there. So suppose this is A, and or we may denote it by S, and this is uh, something like this is S and this is T. So this part is S, this sine curve, and this interval part is T. Okay. So this is our topologist sine curve, and the interesting thing is that it has only one component. It should be clear why this is this has one component, right? So first thing is note that S is S S is connected. So S is connected, it is clear because S is graph. We know that image of a connected set is always connected. So open 0 1, this interval is connected, and this S, this image set can be thought as image of this space under a continuous map. Just take the continuous map, open 0 1 to R2 defined by f, where fx equal to x comma sine 1 by x. So this is image under a continuous map, therefore S is connected. And note that T contains the closure of S. So if you take the closure of S, so it is clear that whatever point you choose, the neighborhood contains infinitely many points from this sine curve, because it becomes denser and denser. Okay. So explicitly I can also write uh, an element. For example, take this some point like this, and take any open ball around this point. So this is a point P. Then P comma 1 by n, it has infinitely many points from the sine curve, this S, from this image of the sine curve, right? For example, 1 by 2n, 1 by 2n comma we need to we need some kind of shift, because it is clear that sine x, whatever point we choose, P from close 0 to 1, right? So sine P is something like this, 0 comma P. Maybe this is a better notation. Instead of P, let me denote the point by 0 comma some P. Then it is clear there exists some y such that sine of y equal to P, right? It is always the case. And moreover, you can write, sorry, this is not sine x, this is actually sine 1 by x. Otherwise, otherwise there will be nothing like this. It will be some uniform sine curve. But as 1 by x is there, the frequency will be larger and larger. That's why it becomes dense. So let me consider the point origin. Origin is more easier to see. Okay, if we choose the point, the neighborhood around 0, 0 comma 0 1 by n, then you can always choose open ball around this origin. Then it is easy to see that 1 by 2n pi, choose x equal to 1 by 2n pi. So 1 by 2n pi is strictly less than 1 by n. Therefore 1 by 2n pi. So this is, if we take this as 1 by n, then 1 by 2n pi will be strictly less than 1 by n. So this will be something like this. And the, if we apply 1 by 2n pi, then sine 1 by 1 by 2n pi, which is 0. Sine 2n pi is 0. So 1 by 2n pi comma 0, that belongs to this b00 comma 1 by n. Therefore origin belongs to this origin belongs to closure of S. That is, this open ball always intersects with some point in S. This point belongs to the sine curve, and it intersects. Therefore, it is clear B00, this open ball around origin, it intersects with S. This is the definition of the closure, right? So therefore 0 belongs to the closure of S. Similarly, you can prove there are those kind of thing we need to consider, that sin x takes values between 0 comma 1. So we need to use those facts to prove that instead of 0, whatever point you choose and whatever open ball you choose, it always intersect with this sine curve, image of this sine curve. Okay, so from if you can prove that, then it will be clear that this minus 1 comma 1, sorry, this is not 0 comma 1, let me take minus 1 comma 1. 0 1 is also fine, but I'll choose the whole everything. So S closure is actually S union T. Okay, it is interesting to prove prove that. I have only proved 0 belongs to S closure, but using the same idea you can prove that S closure is nothing but S union T. S union T, and there is another point. So instead of open 0 1, let me denote it by close 1. Then closure will be exactly this. Okay. So in this case, S closure is S union T. Therefore, S union T is connected. So S union T is connected, and if we denote this as the topological space X, so X has a subspace topology of R2 relative to R2. Okay, that is same Euclidean topology is under consideration. Then it is clear that S union T, that is X, is connected. In other words, number of connected components equal to 1. But in this example, the number of path connected, intuitively you can see that you cannot connect this y axis part with this sine curve, because the origin is not means x equal to 0, that value is not included. So whatever way you can, so choose a point, that is origin, from this 0 cross minus 1 comma 1, and choose any other point from this sine curve. Then it is clear whatever path you draw, you cannot connect those 2 points. Intuitively it is clear, but we can prove that fact rigorously. Okay, so this proof is already given. The idea is nothing but use intermediate value property. Okay, so whatever path you choose, that suppose it start at this point and it ends at some point from in the sine curve, then intermediate value property will contradict this fact. So this cannot be possible. Okay, and so this is not path connected, but if we choose only this part, that is 0 cross minus 1 comma 1, so that is connected, because that is nothing but homeomorphic to the interval. This is only a line segment. Okay, so it is homeomorphic to interval, and this part, by the same reasoning, this part is image of this open 0 cross 0 comma close 1. But open 0 cross closed 1, this is actually path connected, right? Open 0 comma closed 1, that is path connected. Therefore, this will be actually uh, the image set, this sine curve, that will be path connected. So both are path connected. So that is the partition of the set X. Okay. So this is our T. So number of path components equal to 2. So I have not proved this part, but I have only proved that T and S, those two are path connected. Okay. So X can be written as S union T, and T and S both are path connected. But you need to prove that if we choose a point from S and if we choose another point from T, then we cannot connect those 2 points by a path. So that need to be proven, and that proves the idea is to use intermediate value property. Okay. So from here it is clear that sometimes there are some strict inequality. that is number of path connected is sometimes strictly bigger than connected components. Okay, so let me define few definition. Let me define few notations, that is locally path connected and locally connectedness. So instead of writing individually, I will write in the same definition. So locally path connected or connected. So remove the part path. So a space X is called locally path connected. So before that, X is called locally path connected at a point X. At a point X, if for any neighborhood U of X. So take any neighborhood. Neighborhood means open set around X. There exists a path connected open set, open path connected neighborhood containing X and containing, that is, so there exists a path connected neighborhood V such that V containing U. Okay. So what that means, locally path connected means you can, instead of instead of arbitrary neighborhood, there are some connected neighborhoods. So connected neighborhoods, it is better, right? Connected, it has some extra property. So instead of any neighborhood, you can always use connected neighborhood. That is the feature of this kind of topological space. Okay, so take take the point X and take any arbitrary neighborhood U. There are some connected neighborhood. So you may not be connected. You can be. Can have two different part. This is one part and this is another part. But there exists some connected neighborhood inside this U. Okay. So what is happening around the point X? It may have disjoint kind of neighborhood, but if that is locally path connected, means you can always have some connected neighborhood which contain in this U. So this is locally path connected or locally connected. Just remove the path from this definition. You will get locally connected. So if this is true for all X, if this is true for all X belongs to X, then the space X is called locally path connected. So we have already seen that path connected imply connected. By the same way, we can see that locally path connected imply connected. Sorry, locally path connected imply locally connected. By the same kind of observation, locally connected. Now, what about the converse? So, converse may not be true. Okay, there are some locally connected set which are not locally path connected. And what is the relation between locally connected and connected? How those two properties are related? Locally connected and connected. So those two are also related. That is, locally connected may not imply connected. Connected may not imply locally connected. How can we see? So for example, if we take 0 1 union 1 2, we have already seen that this is not connected. So the interval is broken into two disjoint open interval as a subspace. So this is not connected, but it is locally connected. Whatever point you choose any point. This is 0 1, this is 1 2. Choose any point. You always get a connected neighborhood. So this is x minus epsilon, x plus epsilon around that point, and also containing any arbitrary neighborhood. That is any point. Choose any point from this uh, space X. There exists connected neighborhood. Whatever neighborhood do you choose around a point, you always approximate it by connected neighborhood. Okay. So this is the counter example, which is not connected but locally connected. Now, can we give a reverse kind of example? So yes, we have already actually given. So recall again the same sine curve, same counter example, x comma same topological sine curve. I am just drawing. So it is something like this. So this is actually um, connected but not locally connected. So you can choose the point, the origin. So here you can see that the neighborhood around this origin, it will look like discrete kind of something like this. Okay, something like this point, and there are some strip, that is, just see that you can see that, and those are disjoint. Those, you cannot connect those 2 points. Something, it will be something like this. Okay. So though this is connected, but it is not path connected. Not path, not locally connected. And similarly, it is not locally path connected, because locally path connected implies locally connected. So those are few examples. And another important thing is that I have already said that connected components are actually closed set, but we don't we cannot say about path connected components. So path connected components may not be open or closed. Okay. Previously, we have seen that connected components are closed, and in few cases, connected components are also open. That is, what is the case? If it has finitely many connected components. But similar kind of result is not true for path connected components. So in this example, you can see, so this was our set S, this was our set T. Then uh, so in this example, T is actually okay. So let me modify the definition. So instead of S, so here just instead of open 0 closed 1, take open 0 open 1. So just a little modification is needed. if we choose 0 comma open 1, then S is actually not closed, right? This S is not closed. And what about T? T is not open. Okay, with open 0 closed 1 is also alright. This was so from here it is clear that those two are component. S is one path connected component, T is another path connected component. So the topological space is the topological space. This topological sine curve can be broken into two path connected components. But those one component is not closed, another component is not open. So it is also easy to see why that is the case. Okay. So up to this, is everything okay?
Yes.
Okay. So one interesting fact is that uh, this is not a fact, an important observation or proposition you can say, that locally path connected so if x is so x is locally path connected if and only if path connected components of open sets U are open in X, and this is true for all open set. Okay, so one important property is that if X is locally path connected, then path connected components are open. So in general, path connected components may not be open. We have already seen this may not be open, but if that is path connected, locally path connected, then path connected components are open. Okay, is it clear? So instead of path connected, the same thing will be true for connected. So I am putting this property into bracket. So X is locally connected, then connected components of open set U, those are actually open. So this is an interesting property. Using this property, we get a corollary. So what is the corollary? So if X is locally connected, then path connected components containing component containing x0 is same as connected component component containing x0. So why this is true? Because we have already seen that locally, if x is locally path connected, locally path connected component, path connected this condition. If x is locally path connected, then path connected components of x are open subsets, right? Those are actually path connected components are open subsets. So here we have assuming x is locally path connected. So path connected subset are open, but so suppose this is a path connected component. So this is open subset of x. So this is path component, one path component. So suppose this is not connected, then this can be broken into two open uh, open subset whose union is this component, right? Then what is the contradiction? Can you see? So if this path connected, so okay, let me see what is the problem. Suppose let cx0 is sorry, I was already done something. Cx0 is the connected component. Connected component. Okay, so cx0 can be broken into path connected components. Suppose this is x0 and cx0 can be broken into path connected components. So this is one path connected component, this is another path connected, and several other path connected component like this. Then we have just proved that we have just stated the property that path connected components are open. So all those components must be open. This is open. This is open in X. Whatever components are there, all are open. But if there is such a non-trivial partition, then that will contradict with the fact that Cx0 is connected. Right? If something is connected, we cannot broke that space into open subsets like this. Non-trivial. There is no non-trivial partition like this. Non-empty open set which partition the space Cx0. So this is not possible. Therefore, this connected component must be path connected. You cannot break into several path connected components. Is it clear?
Yes, sir.
Okay. So this is the whole theory of connectedness and path connectedness. So I have some doubt with these two things. So this you should check. So S is not closed. This is cleared, but T is not open. S is not closed because these those will be some limit points. All the points from T, those are limit points, but you should check this. I am not certain. So T is not open. Why this is not the case? Can you write T as some open set intersection with? Okay, yes, this is okay. If we assume T is open, then complement of T should be closed in S, right? Sorry, I am doing something wrong. Okay, so just a small thing. So this need to be checked. I am not certain. This need to be checked. Okay. So this is the whole theory of connectedness and locally connectedness. Okay. So this is how locally connectedness helps. Sometimes if something is locally connected, then path connected components and connected components, those two are same thing. Okay. So let us see some problems. So this problem says which of the following maps are continuous. So we are taking R with Euclidean topology. So and RL means R with lower limit topology. This is equipped with lower limit topology, and this is equipped with Euclidean or usual topology, whatever you say. So can you see which of the following are continuous and which are not? So one way is to see directly that F inverse of some open set is open, but there is uh, more easier way for this problem. So how can you see? Note that F from R to RL, this is if this is continuous. If F is continuous, then what is the property? We know that continuous maps preserve connected components, right? F of connected component will be connected, or F of connected set is connected. Connected subset that will be connected. But what are the connected subset of RL? R with lower limit topology. So the interesting fact is that R with lower limit topology, this is actually uh, what is this called? Completely disconnected or something like this. So here if we choose any 2 points, choose X and choose another point Y, those two cannot be in the same connected components. Why? Because lower limit topology, so this x comma infinity, this is open in RL, and minus infinity comma x, this is also open in RL, because this is actually open in real number, and RL lower limit is finer, so those two are actually open in lower limit topology, right? So from here it is clear that R can be written as disjoint union of these two open sets, and X belongs to one component. X belongs to this component. So if X and Y, those are two different points, Y belongs to one component and X belongs to another component. Is it clear what is happening here?
Yes, sir.
Okay. So therefore, connected components in RL are singleton set, right? So connected component are singleton set means the image is connected set. Since F is continuous, image of a connected set R is connected, so the image should be connected, right? Therefore, from this observation, it is clear F of R will be connected. But connected means a singleton set. So among which of this option the image is singleton set? So it is clear that except this option fx equal to 0, the image cannot be singleton. For example, here for sin x the image will be -1 to 1, right? Image sine of r, that image will be -1 to this 1. Similarly, image of this x square is close 0 to infinity. Image of this identity function, this is whole r. So the only possible option where the image is singleton set is this. And constant map is always continuous. Whatever topology you choose, this must be continuous. Okay, is it?
Yes, sir. I
Okay.
get.
So is R homeomorphic to Rn? Is it true? So this is not true. How can you see? Again, path connectedness property that is preserved under homeomorphism. So if possible, so this is actually not true. So this is actually false. If possible, let there exist a homeomorphism. Homeomorphism F from R to Rn. Okay. So if F is the homeomorphism, F is a homeomorphism, then remove a point. So remove R and remove 0. Okay. So then this homeomorphism, so this F induces a homeomorphism, just restrict over this R minus 0. Remove the origin. So this F restricted to another homeomorphism Rn minus 0. Rn minus F of 0. So I am just removing a point. So this F restricted to another homeomorphism. So this should not be called F, but this is just abuse of notation. So I am denoting it by F. So this is again an homeomorphism. But what is the problem? We can see that this map is actually sorry, the domain is not connected. Origin is removed, so this broken into two parts. Okay, so this is not connected. This is actually disconnected set, but if we remove origin, this remains connected. Okay, whatever point you remove from R2 or higher dimensional R3, R4, whatever point you remove, suppose this is a point, this is F0. Suppose you remove this point, then choose any 2 points. You can completely ignore F0 and you can connect those 2 points. So this will be actually path connected, right? And in particular, path connected means it will be also connected. Okay. So this is connected. So we are getting image of sorry. So for F there is no issue, right? Because for continuity there is no issue, but F is homeomorphism. Homeomorphisms means if one side is connected, then another side must be connected. But this is not the case. Okay. So this is homeomorphism, but it one domain is connected, codomain is disconnected. Domain is disconnected, codomain is connected. This is a contradiction. Because connectedness is a topological property. So therefore this is true. That is, therefore R is not homeomorphic to Rn. That is why it is false. F is a continuous map from S1 to R, then there exists x belongs to S1 such that fx equal to f of minus x. So is it true or not? Let us see. It is true or not. So my claim is it is true. So how do we see that? F is continuous map from S1 to R. So let us consider another function g from S1 to R. Okay, and denote g by this: g of x equal to f of x minus f of minus x. So what is minus x in S1? So if we assume this as x, then minus x means antipodal point. This is our minus x. So the theorem says whatever continuous maps we choose, there exists a antipodal point like this. There exists a collection of a point and its antipodal points such that their image are same. This is the property. Okay, this generalized to more in higher dimension also, but we will only see for this case S1 to R. The proof is different for higher dimension. Okay. So gx equal to fx minus f of minus x. Then let us take one point. Let x0 belongs to, let us choose a fixed point. X0 belongs to S1. Then g of x0 equal to f of x0 minus f of minus x. So if this is 0, then we are done, right? We already, there are several cases. If this fx0 and f of minus x0, this difference is 0, then we have successfully we have a point x0 such that fx0 equal to f of minus x0. Then we are done. So if this thing is greater than 0, then what happens? So if this is greater than 0, then so for this case, this is case 1, which is done. For case 2, what happens? Then g of minus x0, which is f of minus x0 minus f of minus minus x0, which is plus x0. But this is same as minus of gx0, right? So we have assumed this gx0 is strictly positive, then minus gx0 must be strictly negative. But what is the intermediate value property? So IVP says there exists some y belongs to S1 such that, so 0 since 0 belongs to, so minus gx0 is, consider this interval. Okay, 0 belongs to this interval. So IVP says from a connected topological space X to R, whatever continuous function we choose, it attains every value between some gx1 and gx2. Okay, so since g is continuous function, so g attains every value between 2 points from its image. This is the IVP. So only condition is domain should be connected and codomain is real number with Euclidean topology. So from IVP, there exists y belongs to S1 such that g of y equal to 0. But g of y equal to 0 means gy is, by definition, gy is fy minus f of minus 1. So again we have a point such that fy equal to f of minus 1. Again we are done. So again we are done. Now there is another case, case 3. Case 3 is the opposite to the case 2, right? In this case, gx0 will be the first one. This is negative, this will be negative, and this is the positive. So again, by symmetry, the same kind of result is true. Is it okay? I am simply using intermediate value property.
Okay, sir.
Okay. So which of the following are correct? X is path connected. This imply X is connected. Is it true? Path connected imply connected.
Yes, this was discussed.
Yes. So this is actually true. Now, what about the reverse inequality, reverse implication? Connected imply path connected?
Not necessarily.
Yes. So we have already given an example: topologist sine curve. Topologist sine curve. Uh, every connected set in Rn is path connected. Is it true? Every connected set in Rn is path connected. So topologist sine curve, you can see that topologist sine curve is a subset of R2, right? So again, the same example, topology sine curve. This is a connected subset of R2, but it is not path connected, right? So C is also false by the same example. For BC, the same counter example will work. What about D? Every connected open set in Rn is path connected. So D is also correct. Let us see the property. This is very important property. So every connected open set in Euclidean space Rn, that will be path connected. Suppose this is uh, connected subset of Rn. Then, if possible, we can prove in this way. Suppose this is a path connected component. This is a path component. Then we can prove this component. So this is connected X is A containing Rn. This is actually connected. We have assumed this is connected open set. Now, suppose A is not path connected, then consider one path connected component. Okay, so this is a path connected component. Uh, B is a path component. Let B is a path component. Then we will prove that B is open and complement B is also open. So note that A can be written as B union complement of B. So our claim is that B is also open and complement of B is also open. So how do you see that B is open set? So B is open, you can easily see that choose any 2 points. suppose B is a component, so B is a component, path component, path connected. So choose any 2 point X and Y. This is always, this can be joined by a path. So if B, if we write B as component of path component of component of some point X, okay, then any other point Y can be joined by a path like this. Now we'll see that y also belongs to the interior of B. Sorry, we try to prove that B is open. So we'll see, we'll prove that any neighborhood of this point Y also belongs to B. That is, Y is an interior point. Okay. So whatever neighborhood we choose, the neighborhood, it contains some disk, right? And for any point in the disk, you can always join it by some straight line like this. So this is the property of Rn we are using. That for Rn, the balls, any point for using convexity of the ball, any 2 point can be joined by a line segment. This is the property we are using. Okay. So from this observation, you can see that the path component B is actually connected. The path component B is open, and similarly, we can, by the same way, that if 2 points are that is, if a point cannot be connected with X by a line, then any neighborhood of that point also cannot be connected by a line, by a path. Sorry, by the same kind of observation you can. Okay, so B, A can be written as B disjoint union with B complement, and both are open. This is open set. This is also open set. So this is a contradiction, right? A is a connected open set, but it breaks into two disjoint open set, and both are non-empty. We have assumed both are non-empty because uh, then we are getting a contradiction.
Sir,
Yes. Yes. Go ahead. What is your question?
can you explain why B complement is open? I'm still confused.
Yes. So I have assumed B as some B is path component of X. Okay. So take a point from its complement. Suppose Z is a point from its complement. This is a point from the path complement of Z belongs to complement of the path component. Then you cannot connect those 2 points by a path, right? There does not exist any path. I have taken the point Z from the complement of the path connected component. Is it clear that there cannot be a direct path which connecting X and Z?
Yes, sir, that's clear.
Now, if we choose any point, if we choose a neighborhood, okay, open neighborhood like this, then those 2 points can be connected by something like this, right? Some line segment like this.
Yes.
But my claim is that this new point, in the neighborhood, you cannot draw a curve which joins the point, the thing x and this new point. Otherwise, it will also join the point z, right?
Yes.
Okay. So this is the problem, that is both B complement and B both are open. So this is the problem we are getting. So here the openness is used because uh, since A is open, this kind of disk will exist. Otherwise, there may not be something like this. If A is not open, then, for example, suppose this, consider this point, disk, disk with a boundary. Then for those point, for example, a point belongs to the boundary. Here you cannot have any open disk which contains that uh, contain inside this space, right?
Yes, sir.
So for this property, that every point, every neighborhood contains some disk, for this property we need open set. That set A is open. This is needed because of this fact, and we are using nothing but convexity of open neighborhood.
Yes, sir. Now it makes sense.
Oh, great. So this is how every connected open subset in Rn is path connected. So this property is very important. So that's why I have already said that open 01, open 01 is path connected, because this is connected subset of Rn. We already know open 01 is connected. By intermediate value property, you can prove, or there is a direct argument. So this is connected, so that will imply this is also path connected. So that is why this thing is important. Any connected open set in Rn is path connected. Now, again, which of the following are correct? So, okay. So, locally path connected imply path connected. Is it true?
No, it was just, you showed this just now.
Yes, this is no by the same topology sine curve. Uh, Sorry, locally path connected imply. Sorry, let us see. Locally path connected imply path connected. So this is not true. I will create a path connected locally path connected space which is not path connected. So take this space. Again, this closed 0 open 1 union open 1 closed 2. So you can see this is locally path connected by the same argument. Whatever point you choose, there exists a connected neighborhood. Whatever neighborhood you choose around that point, you can always get a connected neighborhood in that neighborhood. So locally path connected is clear, but this is not path connected. This is also clear because this is not even connected. Path connected will imply connected. So this is the counter example. Now, locally path connected imply locally connected. Is it true?
Yes.
So this
Again,
is,
this.
yes, by the same argument, path connected imply connected. By the same argument, we can prove locally path connected imply locally connected. Because path connected neighborhood, that will be also a connected neighborhood, right? Path connected is automatically connected. So whatever path connected neighborhood we choose, that is connected neighborhood. That's why locally path connected imply locally connected. Now locally path connected plus connected, those two imply path connected. Is it true? So we have seen that locally path connected, sorry, sorry, we have already seen that locally path connected imply path connected. This is not true. Now if we add another extra condition, locally path connected plus connected, now can we say that the space is path connected? So this comes from the fact this is actually true. So we have seen for locally path connected space, path connected space, number of connected components equal to connected components equal to path components. So we have already seen this fact. So connected means it has only one connected components. Therefore, path connected components, there will be only one path connected components. Hence, it is path connected. So this is also clear. Now, what about option D? Path connected imply locally path connected. Is it true?
Yes.
So again, there is actually no relation between locally path connected and path connected. Okay. So a space may be locally path connected but not path connected, and vice versa. So this is also not true. Okay. So let me create an example. So always remember this example. This is also an interesting example. So which by which example we have seen this is not true for connected analog. That is, can you give a connected set which is not locally connected? So let me draw. So this is this topology sine curve. So this is actually uh, locally. You can see this is actually locally connected. Sorry, not locally. This is actually connected, but not locally connected, right? Now, one question: is it path connected? So the answer is no. We have already seen it has two components. This is one component, and this is another component. Now, can we make it is such that can we create a space which is path connected using this? So the answer is yes. Just extend this curve in a way such that it joins those two ends. So it joins origin with another end. Then note that this becomes connected, path connected cell, right? Though previously it was not path connected, but if we join origin and another arm, then it becomes path connected, because now you can whatever point you choose from the y-axis, then you can join using this curve, right? Can you see that this becomes path connected?
Yes.
So this is path connected. Path connected. So that this example is modified sine curve, or there is some name. Probably it is called Warsaw circle. Warsaw circle. Or there are some other names also. Topological, or just extended. You can also say extended sine curve. Extended topological sine curve. So this is path connected, but not locally connected. This is not locally connected, and since it is not locally connected, it is not locally path connected. Because locally path connected imply locally connected. So if something is not locally connected, it is not locally path connected. So the only problem is the point in the y-axis. Here you can see the neighborhood contains something like some straight line like this, neighborhood of any point. So those are actually disjoint sets, right? So this will create the issue. Okay. So this is also false. There are some path connected spaces, and sorry, there are some path connected spaces, but not locally path connected, which is not locally path connected. Now again, there is a question which says there exists a topological space with 3 connected components and 5 path components, and the reverse one, 3 path components, 5 components. So is A possible? There exists a topological space with. So can you recall the fact that number of path components, it is greater equal to number of connected components. So here you can see in the first question there is 3 connected components and 5 path components. So it seems like it can happen, but in option B there are 3 path component and 5 connected component, which is not possible. So by this, B is not possible. This is 3 and this is 5. Now what about A? So can we create a topological space which has this property, 3 connected components and 5 path components? So answer is yes. Just use that topological sine curve. Okay. So I may start one topological sine curve like this, something like this, and another topological sine curve in the opposite direction. Okay. Then you can see there are 3 components. One components are due to this part, one component is this part, another means those are path component. There are 3 path components. So let me denote it by S. This is the topology sine curve. This is the means mirror image of this S, which is S dash, or maybe S2, S1, and this is S2 or minus S, whatever you denote, and another line T. So up to this, there are 3 path component and only one component. Now can you add extra 2 path components? just add any thing like this. So this is one component, and this is T, and those are S1, S2. Now we add another two lines. For example, this line and this line. So this is T, this ST. Now this is W1, W2. So let X equal to S1 union S2 union T union W1 union W2. So it has, note that it has only three components. One component is this, and another component is this. So that whole one is another path, another uh, connected component. So it has three components. So one component is W1, another is W2, and another component is S1 union S2 union T. But it has five path components. All those S1 up to all those points are okay. So all those are, but it has five path components. Okay. So it can be generalized. Whatever connected components and path connected components are given, if the number of path connected components is greater, so suppose this is n, this is m, and if m is greater than n, then you always can uh, create a space which has m many path components and n many connected components by similar kind of, just add more and more sine curve. For example, you can also add sine curve here, sine curve, so that to increase the difference between m and n. Okay, so this is how you can create some spaces. Okay, so let me stop here. Up to this, is there any question?
No, sir.
Okay, so that example, that topological sine curve example, you should always recall, remember this example, because this is very important. You can create lots of counter example using this. So, okay, something I down. Oh, yes. If T is actually open, then S will be closed. So it is actually true. That is actually very wrong. Because T is open will imply the complement of T, which is this S, that is closed. But this is not true. Therefore, this is not closed. Therefore, this will be not open. So this is actually correct. There is no confusion. Sorry for this. Okay. So thank you for joining. Let us stop here.
Thank you, sir.